North Carolina State, and he's going to tell us about a different type of dimensional reduction.
Yeah, thanks, Mike. Thanks for coming to my talk. Here's the usual outline of the talk. I will start with some background introduction, then talk about the proposed method, some simulation study and real data analysis, and then conclusion. And this is a joint work with my colleague, Dr. Bundell at North Carolina State. I want to start with this very brief introduction on this model-free variable selection idea. With a large number of variables routinely collected in many scientific studies right now, I guess we all agree variable selection is probably an important component in regression analysis. However, the majority existing variable selection approaches are model-based. That is, we kind of assume the underlying true model is known up to some finite dimensional parameter, or we assume the imposed working model is usefully close to the true model. And there are some potential limitations. That is, we all know the true model is, in most cases, unknown, and the model formulation is never an easy thing to do. And also the assessing the goodness of model fitting can be even more difficult if we want to consider it together with model selection, etc. For those reasons, we here consider a slightly different variable selection approach. That is something we call the model-free variable selection. In other words, we want to consider selection of important variables before we impose any traditional model. Okay, so in other words, we want to do this variable selection without requiring any model. Here I want to make a statement first. That is how we view this model-free variable selection. We think it is kind of more useful in the initial exploratory stage of the analysis. So we are not saying all those model-based selection methods are not good. Actually, once we kind of do this model-free variable selection, then we probably have a better idea about what the true model may look like, and then we can further use the model-based selection to refine the results. Okay. This model-free variable selection we consider here is achieved by taking advantage of this general framework of sufficient dimension reduction that was first proposed by Kurzweil in around 1991, and then later developed by both Kurzweil and Dennis Cook and many others. So in the next couple of slides, I'm going to briefly introduce the background of this sufficient dimension reduction. Actually, in the first several days of this workshop, there have already been some talks covering this topic, which basically makes my life much easier here. So I'm going to just go through this couple of slides quickly, and we want to study this conditional distribution of response to y given a predictor vector x. And what we want to do is we want to find a p by d matrix eta with d usually less than or equal to, actually in most cases much less than p, such that the distribution of y given x is the same as the distribution of y given eta transpose x. Or another way to look at it is given eta transpose x, the response y is independent of the original predictor vector x. If so, then we say we can replace the p-dimensional x now with a lower dimensional, that is d-dimensional linear combinations eta transpose x, and then we can do that without losing any information on the conditional distribution of y given x. And for that reason, we call this sufficient dimension reduction. And there is a key concept associated with this sufficient dimension reduction. That is something we call the central subspace. You can see if we start with this conditional independent statement, this eta is not unique. For that reason, we define a dimension reduction subspace as a space spanned by columns of eta, and then we look at the minimum dimension reduction subspace, which takes the form of the intersection of all those dimension reduction subspaces. And so by this definition, this central subspace is a parsimonious population parameter that captures all regression information. So the central subspace is the main object of interest in our dimension reduction inquiry here. And this structure of the central subspace is actually pretty general. Here I list just some examples here. Like the first one is a single index model or multiple index model, where in that case you can see the central subspace is spanned by those columns eta 1, eta 2, up to eta d. It also covers a heteroscedastic model where in the second example the central subspace is two-dimensional spanned by eta 1 and eta 2. We can also deal with the categorical response. So for example, for the logistic regression, then in the last case, the central subspace is spanned by eta 1. And there have been a lot of dimension reduction estimators proposed to estimate the central subspace. Examples include this famous and long-standing slice inverse regression, and later on the slice average variance estimation, principal Hessian directions, etc. And later on, a little bit more recent proposals, including like inverse regression estimation, etc. Then, before we continue, let's look at just a very simple example here. We generated a response y as the exponential function of a single linear combination of the predictor x, where my x and the arrow term are all independent and normal random variables. And the central subspace in this simple example is one-dimensional, and I generate the data this way, where the eta 1, which has the first two elements, are non-zero, and the rest are exact zeros. Now, if I apply, for example, slice inverse regression or this more recent covariance inverse regression estimator to this simple data, this is the estimate based on one data replication. You can see this estimate actually is pretty close to the true direction. On the other hand, we note that the last four elements, although the numbers are pretty small, they are not exactly zero. So this is actually a common problem with most of the dimension reduction estimators. That is, they produce linear combinations of all the predictors. However, there is no variable selection, and for that reason, the interpretation is also somewhat difficult. Therefore, what we want to do in this talk is we want to do variable selection, and how to do that, and we want to get some kind of sparse estimate of the sufficient dimension reduction estimator, then do the variable selection. And then the next slide actually summarizes the key ideas of our work. So what we do is we first observe that the majority of the sufficient dimension reduction estimators, they can be formulated as a generalized spectral decomposition problem. And then from there, we transform the spectral decomposition into an equivalent least squares formulation, and then we can add the regularization on top of that. And then the focus of our work is to demonstrate that this resulting regionalized sufficient dimension reduction estimation, or this model-free variable selection, can achieve the usual selection consistency under the usual conditions, as in the case of the model-based variable selection. So there have already been a lot of work results developed for example, the multiple linear regression model. We want to demonstrate that those results can be carried over to our context of model-free selection as well. So here are a little bit more details. So as I mentioned earlier, the majority of sufficient dimension reduction estimators can be formulated as this generalized spectral decomposition, where on the right-hand side, this sigma matrix is simply the covariance matrix of the predictor, and the omega matrix on the left-hand side is method specific. Here I gave some examples. For instance, for the slice inverse regression, it takes the form of the covariance of the inverse mean vector, etc. And then under some method specific conditions, we can show this equality, this relationship holds, which basically says we can get information about the central subspace by conducting that generalized spectral decomposition. Something I do want to mention quickly over here is most of those sufficient dimension reduction estimation methods impose the assumption on the marginal distribution of x by requiring x to be, for example, elliptically symmetric. However, most of those methods do not impose condition on the conditional distribution of y given x. And for that reason, we view this whole family of sufficient dimension reduction estimators as kind of model-free approach. And because the variable selection is going to be achieved within this framework, that's the reason we say this variable selection approach is also model-free. Now, starting from that generalized eigendecomposition, it's relatively straightforward to note that we can rewrite that problem as an equivalent least squares optimization. That is, if we minimize the function over the function in red on top of the slide over there, we can get the equivalent solution as doing this eigen decomposition, or if we look at the matrix form directly, we get something as follows here. And then this is actually kind of the foundation of the so-called minimum discrepancy approach, which actually covers most of those SDR estimators. So what we do, we start with construction of this P by H matrix theta with the property that the space spanned by theta is part of the central subspace, and in most cases we expect the equality side hold there actually. And then given data, we construct a root and consistent estimator theta hat of theta. Then we pick a positive definite matrix V and a root and consistent estimator of V hat. Then we estimate this quadratic discrepancy function over here over a P by D matrix eta and a D by H matrix gamma. What it is doing essentially is just decompose that theta matrix to two sub-matrices, and then we say this space spanned by eta hat forms a consistent inverse regression estimator of the central subspace. A lot more details can be found in this paper by Cook and Li in 2005 JASA. Here, just one more quick note. This family actually, this represents a whole class of estimators. Its individual members determined by the choice of those pairs theta and V, and correspondingly theta hat and V hat. So I'm not going into the details of the rest of this slide, but I just want to point out, for instance, for slice inverse regression, we can choose a specific theta and V matrix. For this CRE, we have another choice of theta and V. Okay. Now we are ready to talk about our regularized sufficient dimension reduction or variable selection. So after we get this matrix theta hat, eta hat, and gamma hat, we further introduce a p by 1 shrinkage vector alpha, and then we go to minimize this function over here, where we multiply in front of this matrix eta hat, this diagonal matrix of alpha, and we impose some constraint on the elements of alpha. So you recognize this is actually a L1 type of constraint. Then we solve this optimization problem, and then we call the space spanned by diagonal of alpha hat multiplied by eta hat as our shrinkage inverse regression estimator of the central subspace. And if we look at a little bit more closely on this formulation, we realize that when this penalty parameter tau is greater than or equals to the number of predictors p, all those solutions alpha j hat should equal to 1, and we get back to just a yo-yo inverse regression estimator. However, if I decrease the value of tau, some elements of my alpha j hat were equal to 0 exactly. What it will do in turn is to shrink the entire rows of eta because of this structure, this diagonal alpha hat multiplied by eta. Just a few more quick notes. This is a generalization of the shrinkage slice inverse regression estimator, and it is closely related to the non-negative Garrot that was proposed by Bremen. We use some information type criteria to select the tuning parameter, and we say this estimator achieves simultaneous dimension reduction and variable selection. Now this slide, I just want to mention quickly the optimization of this problem turns out to be fairly straightforward if we rewrite that objective function, and we can turn it into a kind of standard lasso type problem. So we can use any existing lasso algorithm to do the computation. So take home message here is the optimization is fairly straightforward. Then recall the goal here is we want to do variable selection, and then, as I mentioned earlier, we do not impose any traditional model. So we do need to be a little bit careful here to say, what do I mean by variable selection without any traditional model? So here is a more rigorous definition of the variable selection without a model. That is we want to partition my predictor vector x to two parts. I want to find the smallest subset of the predictors. I call it x subset A, such that given xa, the response y is independent of the rest of the predictors. So I think this is more or less a very intuitive definition in terms of variable selection. Of course, the next question is, does this A exist? And if so, does it exist uniquely? And the good news is this subset A uniquely exists as long as the central subspace exists. And since we always assume the existence of the central subspace, so this subset A is kind of population parameter is well defined. And the next result, first observed by Cook 2004, basically connect this subset A in variable selection and the basis of the central subspace, which it says is basically as following the rows of the basis of the central subspace that corresponds to all those inactive or irrelevant predictors. Those rows should all be zero vectors, and vice versa. That is, all those predictors whose corresponding rows of the central subspace in the population label, those are equal to 0. All those predictors belong to this inactive set. Now, given this observation, now we can partition my theta, first of all, to these two parts, theta A and theta A complement, and I can redescribe my subset A as those rows which have some elements in the corresponding partition, has some non-zero elements over there, and I can define my estimate A hat, which has some rows, which has non-zero elements in those rows of the shrinkage inverse regression estimator. So now I have a kind of population parameter A there and my estimate A hat. And given all those information, we are ready to talk about the main theoretical result. So what we found is basically, as long as our initial estimator theta hat is root and consistent, and as long as this V hat matrix is root and consistent, and by imposing those usual conditions, which are also assumed in the model-based variable selection, we get the following results. So in words, these two results say, first of all, we can consistently select all those active or all those relevant predictors with probability approaching to 1. And second, for those truly relevant predictors, the basis estimate is still root and consistent. Okay. Since I'm kind of running short of time, I'm going to go through the simulation a little bit fast. But first of all, if we revisit this simple motivating example I mentioned earlier, where we know the last 4 elements should be exactly 0 in the population, if we apply this shrinkage CRRE to that data, we did get the last 4 elements shrunk to exactly 0. And then we did a little bit more comprehensive simulation study. I considered a nonlinear model of this form taken from an earlier SIR paper. And in this case, the central subspace is spanned by these two vectors, eta 1, eta 2. And I vary the number of the non-zero elements in each direction and see how this proposed variable selection method performs. And you can see this table summarizes the average results based on 100 replications. I report the number of true number of active variables and the estimate number, which you can see are pretty close. The true positive rate is pretty high in all cases, and the false positive rate is relatively low. And the last column report how well this basis estimate is. And again, you see the method works reasonably well. And then we try this to a real data quickly. The response is log and the car price in log scale. We have 13 predictors. I just want to show this plot. You can see when I change my value of regularization parameter tau, and on the vertical axis I have my shrinkage parameter, then eventually once tau reaches to the number of predictors, all those become 1, and this red vertical line corresponds to the tau which was selected by our information criteria. So that's most of our talk. And for more details, you can find the materials of this talk in this paper, and this is partly supported by an NSF grant. Oops. Thank you very much.
Well, maybe Lexin at the coffee break and